pointer. Okay. So we are SARA. We are a small company based in central Italy. And we are operating since several years because we are a handicraft company. But from about the year 2000, we focused only on seismic equipment. We had the experience on electronic, but from 2000 we based it on seismic equipment. And until now we served more or less these numbers. So we have some hundreds of clients worldwide and manufacture over 5,000 seismic units, including accelerometer, digitizer, etc. And over these 5,000 units, there are about 750 seismic recorders and also 16,000 accelerometer transducers that also Sanlian use from us. We commissioned also geophones because we deliver geophones for geotechnical or geophysical exploration devices that I will show you later. And also several borehole units because we produce several borehole units for the oil and gas monitoring. Also we have, we can say, quite a large portfolio of software processing software suites, and we will show you a little later. We have clients mostly worldwide, especially in Latin America, and of course Europe, Turkey, and Spain. So now what I'm focusing on this presentation is for the applied geophysics and microseismic monitoring solutions that we developed during the years. We have tools for soil exploration, and it's very important, and also the recent earthquake in Turkey demonstrated how much important it is to know how is the soil before reconstruction. So we have instrumentation that allow the geophysicists, the geologists, and engineers to comply the building codes before the construction. The building codes comes from, usually used worldwide, comes from California. So in California, the building codes started several years ago. Tells that you have to determine the elastomechanical property of the soil of at least of the first 30 meters from the surface. So we provide the DOREMI, the GeoBox, and also downhole probes and processing softwares. What is the DOREMI? DOREMI is a portable geophysical seismograph, multi-channel, and that have the peculiarity to have the digitizer near the geophone for the best data quality. Probably it is not the most robust system in the world because there are many other manufacturers of exploration seismographs which give very high performances, especially in the desert or in harsh environment. But this instrument has been very appreciated because digitized very near to the geophone. And the less is the length of the analog cable, the better is the signal you get out from the digitizer. And so also we have in this system a modularity because you can purchase one channel by one channel. You can compose like in a daisy chain, like the instrument presented for the bridge monitoring, which is the datum. You can connect in a chain many units. So you can combine your seismograph according to what your needs and budget. And during the time, we also have an opportunity to translate the managing software in Chinese. So if somebody in Taiwan wants to use it, it's easier. Yeah, and another tool that we developed for, not developed, but I mean, we produce and developed for this specific survey is the GeoBox. The GeoBox is a special tool for performing Nakamura method surveys, HVSR. HVSR, for who don't know what is this method, is a methodology which perform the frequency domain analysis of the three components seismograph using ambient noise, so using the noise which is always present in the ground, and divide the spectrum, combined spectrum of the two horizontal components by the spectrum of the vertical components. I don't know if it is possible to zoom on the is this the laser? Is here? Okay. So it's not so visible here, but this yellow curve is the ratio between the horizontal over the vertical spectrum. And this put in emphasis, according to the Nakamura, Yutaki, I think it's Yutaki Nakamura, I think, is from Japan, which found that this is a very valuable indicator of the soil stiffness and soil capacity to produce amplification during earthquakes. So in this case, in this frequency, about 4 Hertz, there is an higher capability for the soil to produce an amplification in case of earthquake. It's interesting that also this method can be used to estimate the bedrock depth in a very fast way. It is the frequency of the peak we find in the HV is related to this formula, to this equation, with this Vs is the velocity of the S wave of the one layer of soil, divided by 4 times the depth of the thickness of the layer. So you can determine the inverse formula using the Vs, if you know, and calculating from the frequency. So you can calculate the thickness of the layer, more or less knowing the velocity of the surface waves of the first layers. You can determine the depth of the bedrock. This is not an exact number because, of course, the property of the Vs, I mean the Vs value of the layers of the soil are not always well known, but with some clue, maybe the geologist knows more or less what type of the soil is, that they can infer how much more or less is the Vs, and then you can determine quite accurately the thickness of the first layer down to the bedrock. Also, we produce for these applications a downhole probe, which is used to determine the velocity of the soils using, of course, a borehole, a hole in the ground, and then you energize from the surface. And with a seismograph, that can be, for example, the Doremi, you can measure the travel time from the shot to the receiver and determine in this way the velocity of the rocks or the soils that you have below the surface. For this instrumentation, we developed a complete suite of soil exploration software. So you can use these tools for refraction surveys, so to make a kind of tomography of the subsoil, or using just surface waves using MASW method, MASW. Maybe you know this, is quite common worldwide. And also we provided interesting tools to use reflected waves from surface. So if you energize from the surface, you generate elastic pools that go down and be reflected by the impedance contrast of the soil when the waves go down and come back. You can determine several mechanical properties using these tools. For example, the most simple is the HVSR analysis. There is a specific tool for this. And so you can have your stratigraphy, inferring the stratigraphy. You can put your stratigraphy and see if the stratigraphy you put, it's a synthetic curve is generated, and when the synthetic curve matches the experimental curve, you have a good chance to have picked the correct stratigraphy. Of course, you have to be a geologist, have to have some experience on how the soil behave on this. We have the software to analyze the surface waves and also obtain a stratigraphy from analysis of the surface waves. Downhole analysis, of course, for the determine, of course, the VS30 or VS equivalent characteristics of the soil, like Poisson ratio, geophysical density, shear modulus, Young modulus, etc. We also, the suite is also composed by a tool to analyze in refraction. So you can reconstruct or imaging the subsoil in 2D. The others are all 1D. And this is an interesting tool which could be used to find water. It's a kind of quite innovating method, because in a simpler way, without knowing exactly the reflection methodology, you can, using just a small number of geophones in a single point. You can see the geophones here in the picture. So you shot with a small hammer, and the reflections that comes out give you an idea if the waves that are coming back to the surface has been reflected by some granular soil. If there is a granular soil in one, maybe 100 meters, 200 meters, whatever, they reflect with different frequency patterns. So the software put in evidence this frequency pattern, which is coming from granular soil, and the granular soil most probably can contain water. So you can determine the probability that in your soil there is water. Because if there is a granular soil, the probability which it contains water is high. If it is solid, almost not. And of course, we also make a more efficient and more complete software for reflection, 1D, which make the reflection methodology, which is quite complex and based on the oil search company, to determine the soil properties using, for example, P waves or S waves, depending on what you prefer or what you need. And the important thing that this method is that you can reach a proportion of depth and length. I mean, the depth of the investigation and the length of the seismic line is more or less 1:1. So if you want to go down 100 meters depth, you probably just need 100 meters seismic line. For the other technique, like refraction or like MASW, the ratio is much higher. I mean, for refraction, to get 100 meters depth, you have to go at least 300 meters long in a seismic line. For the reflection, it's the seismic length, it's less demanding. So it can be an opportunity. Okay, and this is what I presented for the geophysical investigation. And the other example is for the tools for seismic and microseismic monitoring. We have comprehensive sensors and recorders manufacturing for high-resolution sensor, high-resolution recorders, borehole, post-hole sensor, or hybrid sensor, and I'm going to show you. So this is our recorder, which is now available also in not only in the ruggedized box, but also in a more less expensive housing for indoor use when the rugged housing is not necessary, and also available recently introduced in a resolution higher than 24 bits. Not for very high sampling rates, but we can have 24, 26, or if you want, also 32 bits. It is compatible with all the seismic software, like SeisComP, very common in the Asian market, of course, because it supports seedling. And it is very, very efficient with geophones. It has an ultra-high resolution. It can detect, using simple geophones, displacement of few nanometers in the band of down to 0.2 hertz using geophones, not using broadband sensor. I mean using simple geophones, because it has really high quality for the low frequency signal. And also, thanks to it has been also approved by, thanks to Jin Seok, it has been also approved for the Kingham authority, the SLO6 6 channel. Then in the same box, we also provide a solution for weak motion with sensors inside. So it is named Wellbox and the Wellbox Hybrid. The Wellbox Hybrid is a new sensor. We introduced it this year, which it has not only geophones or seismometers inside, including digitizer, but also include a MEMS accelerometer, all synchronized. So you have both strong and weak motion in the same box. And this can allow you or allow monitoring network for earthquake to get weak and small earthquake signal recorded very well by the seismometers. And if the shake becomes higher, the MEMS sensor detects without clipping. So you don't lose any information of the earthquake. As I said before, we also produce a series of downhole and posthole sensors. This is one example of borehole carrier with a hole lock. So it has the possibility to lock inside the pipe at any highness. And this type of carrier can carry not only geophones or seismometers, but also accelerometers, FBA or whatever. Regarding seismometers, we also produce since some years a broadband sensor. The bigger one is the observatory grade, so it has a very low self-noise. And the other one in the corner is a compact one. It has been introduced this year, which has a little higher noise, self-noise, but it's much more compact, and it also can be embedded in a borehole sensor. In fact, this is one of the sensor made for the borehole. You have the electronic here, the digitizer over there, the element of the broadband sensor here, and accelerometer on this part. And this is the gimballing system to level this platform. So if you put the sensor in a borehole, the borehole could be a little bit bended because the drilling is not always perfect. So when it is maybe a 100 meter depth in the depth, the tilt have to be compensated. So we have a mechanism to compensate the tilt. This is one of the installation in North Italy. It has been installed this hybrid version because it has accelerometer and seismometer in the same capsule. These are another example of an SSO8 borehole deployment in Turkey for an oil and gas facility. And so after deployed all these sensors, you have to also process the data for earthquake location. So we have in a SeismoWind a comprehensive software suite for earthquake management. So we have a series of modules which can record the data stream coming from the seismometer. It's also compatible with, of course, it's compatible and follow SeedLink transmission standard. So it can get the data and retransmit the data, relay the data. You can calculate the transfer function of your seismometer and connect the transfer function to the processing module. It has modules to evaluate the noise floor of the site, because it's important when you deploy a seismic device that you know what is the seismic noise on the site, if it is properly, if the place can be properly used for seismic survey or not. You have to determine this. So we have these tools. You have the tools to determine the status of health of your network, and etc. For example, this is one of the software, which, for example, this is the recording software, which manage a number of channels. We have systems running 300 channels, 400 channels, currently running in Italy. This is the stream, all the streams of the, each line is one component of the seismograph. And this is the model which, I don't know if this is true. This is a model which can allow you to design how to deploy or where to deploy a seismic station. You can design your network, you can evaluate where the faults are, and also determine the status of health of the system. And we also have, of course, the location software, which works in as auto-location with a number of methods. Even with a single station. Since 2012, we put in operation in our software, because the methodology was already known by decades, using the back azimuth method. So using a three-axial seismometers, you can determine the position of an earthquake. You can locate an earthquake using the back azimuth method. And we can also, using this software, determine the depth using X-ray inversion with ray path, ray path inversion of the wave incidenting to the seismic station. But also the software offers grid search, the cycle method, IPO 71, IPO sampler, IPO ellipse, they all well-known methods available from the scientific community. And it's also real-time deconvolution. I mean, when the waveform arrives to the software automatically converts it to the unit you need to determine the magnitude, for example. So convert to Wood-Anderson and convert to filtering to better picking, the PNS, etc. So you don't have to do almost anything. And if properly tuned, the system can determine the location of an earthquake from one station, only one station, one signal, up to all the stations you get for the earthquake. And you can then have the location. In average, in our region, we are located in Perugia, we are here, and we have, fortunately or unfortunately, a lot of earthquakes, hopefully small, and we are continuously testing the system, and we get the notification automatically from the system within maybe 20 seconds, 30 seconds after the earthquake stroke. We have the notification where it is. And then the location can be improved manually by the operator. That's it. It's finished. If you have a question,